Hey, welcome everybody to Beyond the Scan. I'm your host, Kyle Cooper, and joining me today is Ascensium's Director of Engineering, Bryce Clark. Today we'll be discussing a crusher feed chute retrofit where we use laser scanning, 3D modeling, design engineering, DEM simulation, and deviation analysis to reduce installation risk. We'll dive in deep. We'll explain our approach, the why, the how. So please don't be shy. Add questions to the Q&A section of the chat, and we'll get them answered. With that being said, Bryce, why don't you go ahead and introduce yourself? Tell us a little bit about who you are and what you do.
Oh, good morning, everybody. This is Bryce Clark, Director of Engineering with Ascensium. We're pretty much the design engineering arm that's separate from AsBuilt, which focuses more on 3D laser scanning, modeling. And so pretty much what we do is we take a deliverable from AsBuilt after they send a team out, they scan a facility, they produce a 3D rendering in assortment of programs, including AutoCAD, Revit, etc. And then we're the design engineering arm as part of Ascensium, where we take that information and we are able to do design work in other programs, including I mainly use SolidWorks. We also use AutoCAD, Venner, in order to interpret that modeling that we have from an exact precision 3D laser scan that's interpreted into a CAD data, and then we transform that into a design if you require those services from us. So, thank you again, everybody, for joining. I'm excited to show a presentation that I put together showing what we've done for a coal-fired power plant, one of the largest in the U.S. That runs Powder River Basin coal. And there's a lot of complex issues that include material handling, dusting, also stagnant material that gets trapped in transfer chutes that run in between conveyors. So Kyle, if I can go ahead and show my screen here.
Yeah, please. Let's dive on in.
All right, awesome.
And Bryce, while you pull that up, what's your background? I mean, how long have you been doing this type of engineering work, and is it relevant to your professional background?
Oh yeah, so I've lived in Fort Myers, Florida for the past 15 years. Jason Schwartz and Jason Atkins, I've worked for them since probably 2011, and we service a multitude of industries between the power industry here in the southeast. Also, we've done very interesting projects for iron ore processing facilities, roofing, and concrete, asphalt. So my main focus is again interpreting the data that AsBuilt produces, and then in the form of a CAD rendering, and then also having the 3D laser scan data to see everything in a realistic view, and then doing my design work around that. So I mean, 15 years ago, this laser scan technology was very it was very new. It took about 20 minutes to a scan. Economies of scale have taken place where we could do a lot more services way more affordably than they were 15 years ago, and in a faster amount of time with emerging technologies. And that's the advantage of being with this company, is that between AsBuilt and Ascensium, I've had the experience watching this industry growing from when this technology was very revolutionary and new, and also trying to figure out how to fit that into a 3D environment. So I've had the privilege of watching this industry grow from the beginning, and staying on newer technologies with the support of the Ascensium and AsBuilt team, and our founders believing this technology over a decade, and they both have over a decade of experience with I mean, 20 plus years in engineering and sales and understanding like how to make sure that we can implement this into very heavy industries where there's very high risk projects that require like very high precision in the form of laser scanning and then engineering experience. Hopefully that was a decent enough introduction. Yeah. Still trying to
You're good.
figure out how to share the screen here. Okay. Can you see this?
We got it.
All right. Awesome. All right. So what everybody here is who's attending is seeing on the screen. This is a 3D rendering I was talking about. This is a crusher house at a Powder River Basin coal-fired power plant. And so this has been a hodgepodge of many retrofits over the years. So this originally started out as built like so just for context. So, here where you see all the AsBuilt modeling structural in green, there's a conveyor where my cursor is following. If you can see my cursor to the top of the building, there's a magnetic separator at the top here. Kyle, can you see my cursor moving?
Yeah, you can see it. It's a little hard to see, but you can see it.
All right. Awesome. So yeah, there's a conveyor that runs to the top of this building. It drops through this magnetic separator head chute here. So the magnetic separator, it pulls out ferrous material so it doesn't ultimately make its way down to the pulverizer and damage like other like downstream equipment, which we've done many projects like that before, where we replace head chutes that have self-driven conveyors and magnetic separation, and then it gets dumped into what's called like a tramp iron chute and exits the building. So we have several examples of that we can show in future webinars. But here's the motor and gearbox that drive the conveyor. And the challenge of this project is we were retrofitting a building for, it's probably been here since like 1950s or 60s. And this used to have like a surge bin where this magnetic separator would feed to, and then it went into a feed conveyor. And based on the needs where there wasn't really current need for like closer need to like storage capacity, somewhere in the 80s and 90s, they took out the surge bin and took out like a feed conveyor that it was on this floor and ultimately fed a crusher here. So this is the crusher that you can see in green where my cursor is floating around. So there were the remnants of a belt feeder here. And at some point that became obsolete. The plant didn't want to have it anymore, so they installed a direct route here that you can see in green. This is one half of so this is a comparison view showing what they had before, because essentially the equipment and operating procedure in this building is they're mirrors of each other with two conveyor belts side by side that you can see here. Two crushers side by side, so it's like a mirror across the center of the building. So this is essentially what they had before that we ultimately replaced on one side, and then this is the new design. So the problem that the plant was experiencing is that after they removed their surge bin and feeders, they had a direct chute route that you can see here in green that went to the remnants of a head of a belt feeder, and it feeds the crusher down below. The problem is that they didn't have any sort of flow control whatsoever going to this remaining head chute. So this was like a hodgepodge retrofit again, like decades ago. And so they fed material directly after it went through the process of the magnetic separation. There's also a sampler mechanism here. So this is a conveyor belt that they still use. And so that's for sampling. There's a cutter mechanism inside the head chute. It samples coal occasionally, so that gets sent to a lab so that they can make sure that they have enough BTU output. And so that's separate. That was not in our scope. Our scope pretty much started here where this hopper was, and then our goal was to redirect the flow such that the material was spread out evenly over the rotors of the crusher hammers. Because if you have material like focusing going into a crusher, no matter what type it is, uh, if you do not evenly distribute the material in like a thin film across the crusher inlet, it'll end up prematurely wearing like the crusher rotor hammers like over time, and increases maintenance. So this is the new design that we came up with. Like, we did not touch the head chute. There was a hopper belief that below that head chute mechanism that deals with magnetic separation and sampling. We did not have any original drawings that allowed us to know the exact flange connection of that hopper where we were doing our redesign. The problem in the original is that this material just like shot down like at a direct route in this remaining feeder head, and then they put some baffles in there, and the coal stream just hit those baffles and spread everywhere non-directionally. It caused like a big mess. There was not really any flow control whatsoever going to the inlet. And so, like I was saying earlier, our scope was trying to redirect the flow at a managed path, and then go through what's called like a spreader chute here, and then ultimately have a what we call a bypass gate or diverter gate that's flopped back and forth using a deck drive. So during normal operation, this gate here allows for coal to travel through the inlet of the crusher itself, or there's a separate pocket in the crusher for bypass when the crusher's out of service that goes further down to the floor below, which is not modeled here, and then ultimately proceeds to the rest of the system. So we'll show some more interesting screenshots here. I just want to give like a fundamental basis for the design. So we have this is what I was explaining earlier. It's like we didn't have any drawings for like where this existing flange was, where this existing hopper is part of that one of 3 generations of retrofits that occurred back when there was used to be a surge bin, there used to be a feeder going into the crusher, and they replaced it with just a hopper to chute that went straight into the crusher. No directional flow analysis. The current design predated the benefits of 3D laser scan that we have now, and then also discrete element modeling. We're able to actually model particles going through the chute work, which I'll get into later. That's part of the relationship between AsBuilt and Ascensium. So I'm able to take this data that you see here, and I can model multi-million-dollar projects without even having to step in the facility, based on the confidence of being able to have down to millimeter precision of everything in the plant. So I can see this on my computer, and I can tell what the existing bolt flange pattern is from the laser scan data, if I don't have drawings available, and then reroute everything to where it needs to go. So here's like another screenshot. So in order to feed that, you get the flow where it need to be in order to be like spread out and into an even distribution of film across the crusher inlet to reduce wear, as I was explaining earlier. We had to reroute the chute work itself, and we use cool programs like Navisworks and Recap, where we can actually in a 3D space, we can actually import a model and be able to see like in a perspective view of where everything's going. So I had to reroute the chute, and then we used we have faculties with structural engineering, where we can stamp projects if we're changing any structural around the floor. So these red beams here, that's a new support foundation for the chute that's being rerouted through that floor. And then what I was explaining earlier with the discrete element modeling, we use a couple of different DEM softwares where we're able to model physical particles. We assign them a density, a size, like if they have an adhesion and cohesion that we rely on material testing for. We have data that supports coal, limestone, other proprietary materials, and so like each one of these bouncy balls that you see here with this speed distribution, these are actual physical particles that we simulate wherever they're bouncing off a surface or sliding along steel or any sort of liner. This is a program that does millions of individual particle calculations in order to get to that point. This cross-sectional view that you see here is that's an even distribution of the material going through into the crusher that we're trying to achieve. And I'll show this one more time. Yeah, we're able to modify the tonnage, the speed of the belt. This is a simulated inlet here, so we don't need to model the entire conveyor if it's like a 300-foot long conveyor. So this is just showing an inlet box that's distributing 1,400 tons of coal, and we can simulate it as like wet or dry. We simulate the belt speed to where it's pouring into this head chute here. This is a modified head chute here where we're not showing the other miscellaneous equipment like the magnetic separator or the sampling. This is just for purposes of our proof of concept for the retrofit. So again, the reason why we redirected the chute work from what it was is that we're trying to aim for the center loading into that crusher through that bypass gate.
Hey Bryce, real quick, how important was this DEM simulation to the overall design of the new chute? I mean, is this a confirmation of design philosophies and approaches, or is this a critical element to perfecting the final design of what the chute will look like?
I mean, honestly, without this DEM simulation software, there was no point in doing the project. Like, so we go back here. This was just a straight run. So again, this is like the new design. We eventually replaced the other side with the mirrors. So this is what it looked like before. This is what it looks like now. And then the other side was eventually replaced with the mirrored orientation. Yeah, like I said, there was really no point in trying to do this project in the first place without the power of that discrete element modeling software, because otherwise you wouldn't be able to tell which way the coal was exactly flowing. They pretty much just had like a straight drop going to this remnant of a feeder head, and then because like it was pre-wearing out the crusher rotors down below, that's why they had to add some afterthought baffle in here that where the material just hit and then it just exploded everywhere, just to try to make sure that there wasn't like a focused stream of material going to one place. So without having this simulation software, like you can't provide a basis of why you're doing what you're doing in order to minimize not only premature wear along the rotors. Again, we're trying to get that even distribution across them so that there's not premature wear in a focus spot, which is a big problem across coal handling facilities or coal-fired power plants in general. So yeah, this was definitely necessary, and we do like an iterative process where I'm able to make like slight changes in my SolidWorks modeling program in order to get the geometry like just right, so it's being able to feed as it's supposed to, like here, which is reflected in reality. So just to move this presentation along, Kyle, did that answer your question? Or
It did, yes, sir. Thank you.
Okay, great. So this is just showing Yeah, the modeling foundation, the premise for why we do what we do, the fact that we're able to check um, future design and check for any sort of class detection. Like we want to be aware of every single beam, pipe, conduit, and environment and make sure it doesn't run into anything. And this will be a good segue into the next part is the fact, the value that between AsBuilt and Essentium, we're able to check everything, from the beginning and when we're presenting a concept and make sure it's not going to run into anything when it's being installed. Like, so a good analogy that I give is the cost of mistakes from a design as like an exponential relationship. So if you make a mistake at the very bottom or at the very beginning of a project, that it doesn't get caught until like maybe the drawings are produced, like that's there's costs to like rework the drawings, like issue new revisions to the client. And then when you get to the fabrication part, your exponential curve of your mistakes like starts increasing rapidly because oh no, like you caught a design mistake at that point, and then you have to pay for more steel, more welding, cutting up parts because you caught an error later in that process. And then the exponential curve like starts to run off if you're not unable to catch a mistake like during the install phase, where the not only has the equipment already been fabricated, but it's been shipped to the site and people are trying to install it. And so if it runs into like a wall, like a beam or pipe or piece of conduit when you're routing chute work or pipe work, and there's an unanticipated mistake, well then you're really screwed at that point because now you have an entire crew of qualified journeymen standing around and who are unable to do anything because they have to seek guidance back from the engineer and make last minute decisions and maybe have to refabricate parts. So like we are a cradle to grave company with between AsBuilt and Essentium doing this laser scanning process in the beginning and then all the way through fabrication and installation. So I showed the design concept or our design process for that. And then this is what I want to get into is like the fact that, before, like even if our design is like 100% perfect, there's still like a risk in fabrication, like something, being off. I mean, we deal with a very long list of qualified fabrication companies, but as like a check, we also offer services doing fabrication, laser scanning, and analysis. So this is what you're seeing on the screen now. Like that's a part of the a chute segment that's made of rolled pipe with flanges here interconnecting. So this is the original model that we compared against a fabricated piece, sections of rolled pipe installed with ceramic and then intermediate flanges. And so this is the laser scanned representation of that was captured at a fabrication site. And then I'll go ahead and detour from this. This is a program that we call Bloom. So if you can see this, like these were individual pieces of that fabricated chute work that were laid out at a plant. These were scanned in color. So, I mean, you can really see like the high definition here. This is made of like 304 stainless steel. It's lined with ceramic on the inside because as part of our chute designs for coal-fired power plants, like you can't have coal riding directly on steel because it's very abrasive. It'll eat right through it over time. And so like the ceramic that you see on here that's glued in, it's lined with 1 inch thick ceramic that's bonded straight to the stainless steel. Steel and ceramic kind of have opposite material properties. Like ceramic is very abrasion resistant, but it's very brittle. So if you have coal that's free falling down through the chute, if it hits ceramic at a very high impact velocity, it'll break over time because of its brittle properties. But it's very abrasion resistant. So part of our reason why we do the DEM simulation is to make sure that coal is not, or any other material is not free falling through the chute. It's gently sliding across all the surfaces at a high enough velocity so it's not potentially causing buildup and plugging up the chute. Uh, uh, sorry, like a low enough velocity where it's building up and plugging up the chute. We keep it just fast enough and gently flowing through the system, so it's wearing on the ceramic in its intended location. We also locate the ceramic too, based off that DM simulation software, so we're not overlining the chute and costing the customer more money where it's not necessary, but being able to predict that exact path of material flowing through. So we're able to take our original 3D model here that you see. So these are the individual scanned parts that you see here in the photorealistic color. This is the spreader chute that I was speaking of earlier that helps spread out the material going into the bypass gate and then the crusher. And the cool part is we're able to do like a heat map and overlay the each of the individual scan chute sections with our original 3D model. So like here, what I'm hiding and unhiding is our original 3D model, and then that's the scan overlaid. We use this program called Bloom in order to check our 3D model design against what's actually scanned in the shop. So this heat map, like green is within like 1/16 of an inch, and then if you start seeing like heat pockets of red, that's where it's off. This is showing red over here just because the ceramic lining in the grouting. Sometimes, like if there's flexes in the steel, depending on how the chute's laid across like a long distance, which we account for and not really worried about. But I'll get back to the presentation so you can you guys see that comparison step by step. So we're not only looking at the 3D model here. This is the laser scan rendering at the fabrication shop. We're able to overlay those and check a heat map. Like, so this tolerance scale is we can set whatever the max acceptable deviation is between 0/16 of an inch or whatever you want the top level to be. I usually set it between usually like 1/16 of an inch, and then past an inch shows red. And we evaluate this as acceptable tolerance. I mean, another thing you have to consider is it's not just like the overall geometry of the chute itself, but the flange, like where you have flanges here, like this round flange that's clocked at a certain way. So imagine, looking back here with this, if one of these flanges was not clocked or rotated at the precise orientation that it needed to be per the design, it could throw off this entire orientation. I mean, if it were even like an eighth or whatever, like one or like a few degrees like off center between each of these round flange orientations, it could totally throw off the trajectory of the chute work. So that's the other thing that we're looking at here, is it's not only the overall bolted together geometry, but like even these holes here being clocked at the right pattern. So we check for that too, so making sure that those holes line up exactly where they need to be, given a complex piece of geometry. So the other thing here, like this is showing the in reality at the fabrication shop, showing the ceramic liner installed. And so if we pick up hot traces of any sort of deviation. Like it's usually because there's grout in there. We know that's happening, but you can see how precise this laser scanning is. Like we don't model this bead of grout in SolidWorks. It's not necessary. We just like show a cutoff line, but you can see here like the grout that joins the steel shell and the white ceramic. Like we're able to actually pick up that deviation in our as part of our analysis. That being said, so since we're able to cover, any potential costs and mistakes, like even doing that fabrication analysis, this is a proof of concept, like showing, all right, here's the actual chute installed. So going back to that picture I showed, this is what we saw in the model, the 3D rendering. And this is showing the actual process of being installed. Pretty happy with that. This was a seamless installation. Everything was predicted ahead of time using the power of the 3D laser scanning, the being able to check the design in the context of the point cloud. And then at every step of the project went within like a fraction of an inch of where it needed to be. No issues whatsoever. So yeah, these are just some fun side-by-sides showing what we were able to see in the model, like overlaying the conceptual design that I produced against the point cloud, similar views like during the installation. So yeah, I mean, the long story short of this is everything ended up where it needed to be.
Bryce, was this done during the shutdown, or kind of when was the scanning and the installation done?
Oh well, the scanning was done like during before the design phase. So this is showing what you see on the screen here. This is when we were first contracted to do the project, and then this is showing the design I put in to reroute the coal in order to do its intended process of avoiding premature wear and dusting, and also doing like smooth flow and increase the lifespan of the system. So this is at the design phase right after the laser scanning, and then this is the end result probably like a year later, at least, when this was eventually installed. So
Bryce, got a couple,
again, yeah,
I got a couple questions for you coming in. First one is
sure.
you mind going through how the chute design process helps with dusting?
Yeah. So okay. So in a coal fired power plant environment, I mean, we've been doing this for like the past like 15 years. Like you can't just have material free falling through any building or any long long route whatsoever. Like I'll show like a similar DM project in this plan. I think that would be a helpful visualization here. So if I were to go to, I'll find one. I'll find like a generic project here. Yeah, because this is more unique. This isn't like very typical for what we normally do at these types of plants. I'll give like the most basic example here.
Okay. Yeah, and a second question, we can tackle that in a second, but it's what specifically did the client get from a deliverables perspective? What all do they receive outside of the I know we typically deliver the scan data, the reality capture, the 360 images. Do they also receive the video of the DEM simulation and?
Oh yeah, yeah, absolutely correct. So all right, so at a fundamental level here, like this is what we're doing. So again, what I was showing in the example or as part of this presentation, like that is like a very like complex, like very site specific application. But what we're doing here essentially is this is like a basic 90-degree transfer. retrofit. So our specialty here is where this used to be like a boxy head chute and load chute, where there was no flow control whatsoever. So pretty much like this is the head pulley, this is the tail of the conveyor. This is like a typical 90-degree transfer system. What we're doing here is we're predicting using the DEM simulation software the precise flow path of the material and guiding it gently, kind of like a water slide at a theme park, to make sure that the material is very gently transferred from one point to the other, and then also center loading the belt down below. So if you were to just allow this material to free fall from one conveyor to the other, and splash at the bottom, I mean, you would see these particles up here at the higher red velocity. We're trying to smoothly control the dynamics of the material so that because if it were in free fall and hitting the bottom of the belt, it's pretty much just dispersing air and dust, unless you're able to contain it with either like active or passive dust control throughout the surrounding environment. So we're trying to prevent entrained, induced air, and keep everything as like a tight, evenly distribution stream in order to load that conveyor. So, I mean, if you go on our website, ascensium.com, in addition to asbuilt.com, like you'll be able to see examples of that. So, and then, yeah, again, not only would the drawback of allowing this material to free fall and causing dust laden air to spread throughout the environment, we're able to make sure that the material is slowly riding along ceramic surfaces, which again, they're susceptible to impact, and their purpose is to allow for long-term wear abrasion, and that overall extends the lifespan of the system. The dangers of allowing coal to free fall from one conveyor belt to the other and allowing dust laden air to spread throughout the plant, it might not be obvious in some places versus other, but the slow accumulation of dust collecting on surfaces, being expanded in the air. I mean, there's multitude of like health issues with that. It can cause an explosion. It can cause an explosion if like the air like touches any sort of hot piece of equipment. If you look up the terminology like combustible dust, we do perform like audits for that to see how what your danger level is in a facility if air laden dust is like accumulating throughout the plant and causing areas of concern. It's not only health risk of explosions, it's also like a mess that you have to clean up like over time, depending on how like prevalent it is. So yeah, that not only applies to coal where that's a risk that's actively monitored, like across the globe, but it applies to a variety of other different industries. Like sugar too is believe it or not explosive. There's multiple examples of explosions occurring at sugar plant facilities. Like, I mean, even like dog food, you wouldn't expect to have combustible dust issues that lead to explosions, but yeah, that's very prevalent in every industry, and that's what we're here to help prevent, through again laser scanning, through material testing, simulations, and ultimately a design that will fit where it needs to be and perform as expected.
Yeah, I appreciate that. And I did not know that. So you learn something new every day. So with this project, what was the end outcome with it? What was the installation like, and what was the end customer's perception or feedback at the close of the project?
Well, I guess you could say like the proof in the pudding is these pictures here. I mean, you can see here the installation went exactly how is anticipated, being able to see ahead of time where things are going. Like this is a continued side by side of everything going in. So that's that, this is showing that we had to install a new structural to help frame in the spreader chute. That's what we saw up there before. So this is the remnant of that feeder that used to be here. Just the head remaining. The surge bin used to be over there. That was generation 1 or 0, whatever you want to call it. And then after the client got rid of that or decided to get rid of that system, they put in just a straight chute here. So we're dealing with like multiple generations of like trial and error and trying to make sure that our last trial is the ultimate one that will be there like a very long time, or definitely for the life of the plant, or who's ever dealing with the crisis at the moment. So yeah, I mean, you can see that. There's the other side by side comparison. What was there before? What we put in. I mean, even down to this Beck drive here that it flops the gate back and forth. We're able to visualize that. Do the mechanical engineering required to make sure it's going to provide enough torque and force in order to flop the gate with the burden of coal falling on top of it. And then there's the reality of how it went in after a year later, mounting it to the ground. So we're taking all the useful information that AsBuilt provides and going above and beyond to make sure not only like everything fits where it's supposed to be, but mechanically performs as it's supposed to, with mechanically and structurally coming up with a sound design so that the customers client or customers like satisfied with the end result performance. And we usually say no news is good news. So after this went in as is, we didn't hear any like when we don't hear like immediate feedback, we have to like cry for information. No news is good news. It performed to expectations, and then when we follow up with the client, they're like, "Oh yeah, worked out. It did what you said it would." So that's all I can say. I mean, at that point, I think there was another question about in terms of a deliverable.
Mm-hmm.
From this cradle to grave process, we're providing not only access to laser scan data, but we can the 3D modeling here. I mean, there's other items in this plant that are relevant outside this one application. Like you can see here, all sorts of electrical equipment, stairwells, lighting. Having an accurate digital twin of any sort of building at your facility is very useful to have. So not only can we use this information to do the specific coal handling project, but there's a wealth of information here that's captured that we can use for any sort of engineering or mechanical, electrical, plumbing application. So you're creating a digital twin, and then your opportunities are endless after that of what you want to change. And
Bryce, I was going to ask you, I know we're coming up on time. Is there any last minute comments, statements or anything you want to share regarding this project, the outcome, the process, or even just the engineering approach?
I mean,
you went pretty deep. You did pretty well. I'm not saying you missed anything.
I'm hoping I went deep enough, but yeah, I mean, this, like as complicated as this looks, maybe to somebody who's never seen this before, we have decades of engineering experience and being like early adopters of this technology, where it's like something like this is not like that difficult for me to produce, like given the stakes. Like that, I'd be a lot more worried designing a project like this or any other type if I was relying on drawings or field measurements. So I mean, we have a very qualified team of scanning technicians that can go to for your facility and capture every single millimeter of information. And I feel very comfortable with the level of the quality of information and accuracy that AsBuilt provides, leading into the design decisions I have to make, and especially for where in a coal-fired power plant like this or any other industry where mistakes get expensive very fast. I'm used to at this point, like I'm not allowed to make mistakes. That's pretty much my job description. Do not make mistakes, otherwise you're going to be the first to get a blame for everything. But it's like a project like this, I view, it's fun to do. It's challenging. I really enjoy this type of work, and being part of like our companies that are like the pioneers of laser scanning precision and accuracy, and then I can sleep very well at night knowing whatever I come up with, I don't claim it's going to be perfect, even though I strive to be perfect. But even if it's trial and error, I know exactly what I'm conceiving is going to end up where it needs to be. Great. With confidence, without not running into anything, and being exactly how I expect. No surprises.
No surprises. I like it. Well, we do have a PDF version case study of this project. And so if anyone does want more information on that to share with friends, customers, clients, just contact your authorized AsBuilt representative to get access to that PDF. And this is why we started Beyond the Scan, right? Delivering the point cloud files is only one piece of the picture. It's really what happens once you get the scan data in place. And over the last few months, as we've had these Beyond the Scan webinars, we've showcased different technologies and different applications and different projects and use cases where, getting the point cloud is just the first step in a longer process. And, it can entail everything from, designing retrofit chute works with DEM simulation and deviation analysis, or it can just be producing, as-built documentation, 2D, general concept, layout, arrangement, whatever it be. Getting the scan data is only the first step in it. So I think that's what really differentiates us, but also having the relationship, with our parent company, Ascensium, being able to guide, projects from soup to nuts all the way through with the different technologies and the resources. That's what makes us different. And that's what I'm very proud of over here. All right.
Well,
thank you. There's no other questions, or go ahead, Bryce.
Oh yeah, thank you very much, Kyle, for putting this together, and thank you for everybody's time. Just reach out to Kyle if you have any other questions or want to set up a one-on-one meeting or group meeting where we can help achieve what you need to.
Absolutely. Thanks, Bryce. Thanks, everyone. Have a good one.
All right. Thanks.